In the previous lecture, we have studied about the first come first served scheduling algorithm, and we have seen how it works, and we have also solved some problems in first come first served scheduling algorithm. We also saw that it was very easy to implement, and also we have seen that it had some disadvantages. Now moving ahead, in this lecture we are going to discuss the next scheduling algorithm, which is the shortest job first scheduling. So from the name itself, it is easy to understand that shortest job first scheduling means the shortest process, or the process that will require the CPU for the shortest period of time, will be the first one to get the CPU. So in case of FCFS, the process that comes first was the one to get the CPU regardless of the length of that process. But in this, the length of the process matters. That means the time that this process will take in using the CPU will matter, and the shortest process, or the shortest job in this case, will be the first one to get the CPU. So it says here, this algorithm associates with each process the length of the process's next CPU burst. So when we say shortest job first scheduling, we don't actually mean the entire length of that process or the entire time that the process is going to take. But what we actually mean is the length of the process's next CPU burst. That means the next time this process is going to use the CPU, how long is it going to take? So for the next CPU burst, what is the length of that process going to be, or how long is it going to use the CPU? So based on that, the processes will be assigned the CPU. So the process having the least next CPU burst will be the one to get the CPU first. And this pattern will be followed for the remaining processes as well. So when the CPU is available, it is assigned to the process that has the smallest next CPU burst. So this is what I just explained. When the CPU is available, the process that has the next smallest CPU burst will get the CPU, and then this pattern will continue. Now there may be a question that comes to your mind. If two processes having the same length arrive, then which one will first get the CPU? If there are two processes waiting for the CPU and both of them have the same length, then who is going to get the CPU first? So in that case, if the next CPU burst of two processes are the same, FCFS scheduling is used to break the tie. So if that kind of a case arrive, if the next CPU burst of two processes are the same, then FCFS scheduling is used to break the tie. So that means if two processes having the same length are waiting for the CPU, then this shortest job first cannot be applied because they are both having the same length. So in that case, FCFS will be used. That is first come first serve scheduling that we have discussed in the previous lecture will be used to break the tie. That means the one that arrived first will be the first one to get the CPU, and then the next one will get after that. So that is how the tie is broken in case two processes having the same next CPU burst are there. So another very important thing that we need to know is that the SJF algorithm, that is the shortest job first algorithm, can be either preemptive or non-preemptive. So we have already discussed the meaning of preemptive and non-preemptive. So in the previous algorithm that we have discussed, which is the first come first serve scheduling algorithm, we have seen that that was a non-preemptive algorithm. That means when the CPU is being used by a particular process, that process cannot be preempted. That means that process cannot be disturbed until and unless that process completes its execution or goes to a waiting state. No other process can come and disturb it and take the CPU away from it. But in case of this shortest job first scheduling, this algorithm can either be preemptive or non-preemptive. There may be cases when it has to be made preemptive, and there may be cases it has to be non-preemptive. So in preemptive case, if one process is using the CPU, then even other processes can come and take the CPU away from it based on some conditions. So we'll be seeing that when we take the examples. So it can be either preemptive or non-preemptive. So as we discussed about the way this shortest job first scheduling works, one thing that we have to notice is that a more appropriate term for this scheduling method would be the shortest next CPU burst algorithm, because scheduling depends on the length of the next CPU burst of a process rather than its total length. So as I have explained in the beginning itself, in this SJF algorithm, though it is called the shortest job first scheduling, we are not considering the entire length of the process, but we are just considering the length of this process's next CPU burst. That means when that process is going to use the CPU for the next time. Why are we saying next time? Because during the course of a process's execution, there may be times it will use the CPU, then again come out for some IO operations, and then again use the CPU, and so on. So when the next CPU burst occurs, that means when the process is going to use CPU for the next time, what is that length going to be? That is what we actually take into account. So a better term for this algorithm would be the shortest next CPU burst algorithm. But in most of the books that you refer, it will be written as shortest job first scheduling or the shortest job first algorithm. But remember that even though it is called like that, it is actually a shortest next CPU burst algorithm. Alright. So since we have seen how it works, now let us see some examples and see how does this SJF algorithm work in case of preemptive and non-preemptive cases. So here we are going to take an example of the shortest job first scheduling when it is non-preemptive in nature. So here consider the following set of processes with the length of the CPU burst given in milliseconds. So here we are given 4 processes with process IDs P1, P2, P3 and P4, and the burst times of these processes are given, which is represented in milliseconds. So P1 has a burst time of 6 milliseconds, P2 has a burst time of 8 milliseconds, P3 of 7 milliseconds and P4 of 3 milliseconds. So in this case, let us see how we can plot the Gantt chart for this and see what will be the average waiting times for this processes if they follow a shortest job first scheduling and if it is non-preemptive in nature. So when we say non-preemptive, we mean that when a process is using the CPU, no other processes can come and take the CPU away from it. Alright, first let us draw the Gantt chart and see how it looks like. So here is the Gantt chart for this set of 4 processes if they are following the shortest job first scheduling and if they have these specific burst times. So let's see. So here what do we have to see? Since it is a shortest job first scheduling algorithm, we have to see which is the process that has the smallest burst time. So that will be the first one to get the CPU. So if you analyze these 4 processes, we see that P4 is having a burst time of 3, which is lesser than all the other burst times of the other processes. So P4 is the one that is going to get the CPU first. This is the shortest process or the process with the shortest next CPU burst. So here in this Gantt chart, we have given the first position to P4. So P4 gets the CPU first. And we are assuming that all these processes have arrived at the same time. Here the arrival times are not given. So we assume that all these processes P1 to P4 have arrived at the same time. So first of all, P4 gets the CPU because that is the one with the shortest CPU burst time. Now, how long will it execute? It will execute for 3 milliseconds. So from 0 to 3, P4 will be executed. Now after P4, which is of 3 milliseconds burst time, which is the next process having the least burst time? So from these remaining 3 processes of P1 to P3, if we check, we see that P1 is the next one, which is having a burst time of 6 milliseconds, which is lesser than 8 and 7 of P2 and P3. So P1 will get the CPU next and it will execute for 6 milliseconds. So 3 plus 6 equal to 9. Up to the 9th millisecond, P1 will be executing. So what are the remaining 2? P2 and P3. Among this, which is the smallest one? It is P3, which is 7. So at the 9th millisecond, when P1 releases the CPU, P3 gets the CPU and it will execute for 7 milliseconds. So 9 plus 7 is 16. So up to the 16th millisecond, P3 executes. And finally, we have P2, which is of 8 milliseconds. So at the 16th millisecond, P2 gets the CPU and it completes its execution at the 24th millisecond because 16 plus 8 is 24. So this is how the Gantt chart looks like for this SJF scheduling algorithm for this set of 4 processes with this set of burst times. Now let us try to calculate the average waiting times for this set of 4 processes. So since we assume that these processes have all arrived at the same time, it is very easy to calculate the waiting time for each processes. We can just see it from the Gantt chart over here. So what is the waiting time for P1? Look at P1. P1 got the CPU at the 3rd millisecond. So that means P1 had to wait for 3 milliseconds because we assume that they have all arrived at the same time. So P1 got the CPU at the 3rd millisecond. So it waited for 3 milliseconds. Now similarly, what is the waiting time for P2? If you look at the Gantt chart, we see that P2 got the CPU at the 16th millisecond. So the waiting time for P2 is 16 milliseconds, and the waiting time for P3, similarly, if you look at the Gantt chart, we see that it is 9 milliseconds, and the waiting time for P4 was 0 milliseconds because P4 was the first one to get the CPU and it did not have to wait. So 0 is the waiting time for P4. So what will be the average waiting time for this set of processes? It will be 3 plus 16 plus 9 plus 0 divided by 4 because we have 4 processes. So that will give us 7 milliseconds. So the average waiting time for this set of processes is 7 milliseconds. Now by comparison, if we were using the FCFS scheduling scheme, the average waiting time would be 10.25 milliseconds. So if we were using the first come first serve scheduling algorithm for the same set of processes for the same set of burst times, then we would find that the average waiting time would have been 10.25 milliseconds. So in the previous lectures, when we discussed about FCFS, we have already shown how we calculate the average waiting times in case of FCFS scheduling algorithm. So I will not be solving this same thing using FCFS scheduling algorithm again because we have already discussed such examples before. So you can try solving it yourself, and you will find that if you solve it, you will see that using FCFS scheduling algorithm for this same set of processes, the average waiting time would be 10.25 milliseconds. So from that itself, it is clear that this SJF scheduling algorithm is better than the FCFS scheduling algorithm. Why? Because the average waiting time in case of SJF was only 7 milliseconds. But if we solve the same thing using FCFS, we are going to get 10.25 milliseconds. So which clearly shows that SJF is a better scheduling algorithm because it is giving a lesser average waiting time. And why is that? That is because if we assign the CPU to the smaller processes first, then that reduces the waiting time for the smaller processes instead of increasing it for the larger processes. So in the long run, we are going to have a lesser average waiting time. So in that way, we see that SJF scheduling algorithm is better than the FCFS scheduling algorithm. So this was the example for a non-preemptive SJF scheduling algorithm. So it was non-preemptive because we saw that when one process was using the CPU, nobody disturbed it until and unless it completed and released the CPU, no other processes were given the CPU. So it was non-preemptive. Now let us take another example of this SJF scheduling algorithm when it is preemptive in nature. So in this example, we are going to consider the SJF scheduling algorithm when it is preemptive in nature. That means when one process is using the CPU, even other processes can come and take the CPU away from it based on some conditions. Alright, let's see. So consider the following 4 processes with the length of the CPU burst given in milliseconds, and the processes arrive at the ready queue at the times shown. So here we have a table where we are given 4 processes again with process IDs P1 to P4, and here are the arrival times of these processes. P1 arrives at time 0, P2 at 1, P3 at 2 and P4 at 3. And this is the burst time of the processes given in milliseconds. So burst time of P1 is 8, of P2 is 4, P3 is 9 and P4 is 5. So all these values are given in milliseconds. So in this case, we are going to consider that this SJF scheduling algorithm is preemptive in nature. So if it is preemptive in nature, let us see what will be the average waiting time for this and how do we calculate the average waiting time for this. So the first thing that we are going to do is we are going to draw the Gantt chart for this. So let us see if we form the Gantt chart for this set of processes using SJF scheduling algorithm in preemptive way, how will it look like? So here is a Gantt chart for this set of processes, and let us see how we have formed this Gantt chart. So if you look here, we have to see what is the arrival time and the burst times. So first of all, we see that P1 was the process to arrive first. So at 0 millisecond, P1 arrived and the burst time of P1 is 8 milliseconds. So if you look here, we may think that there are more processes here which are having lesser burst times. So why not give the CPU to that? But the problem is at time 0, only P1 was there. No other processes were there at time 0. So we directly gave the CPU to process P1. So at time 0, process P1 got the CPU. Now what happens is at time 1, so at 1 millisecond, P2 arrived. And what is the burst time of P2? It is 4 milliseconds. So we see that at time 1, P2 arrived and the burst time of P2 is less than that of P1, which is already using the CPU. So here the SJF scheduling algorithm is going to work because the process having the lesser CPU burst should be the one getting the CPU first. So among P2 and P1, P2 has the lesser burst time. So what will happen? P1 will be preempted. That means P1 will be removed from here. the CPU will be taken away from P1 and be given to P2. So at time 1, P2 arrived, and since the burst time is less than that of P1, which was already using the CPU was taken away from P1 and P2 got the CPU. Now let's see. P2 begins its execution. Now when P2 begins its execution, it has to execute for 4 milliseconds. So let's see. It is executing now. Now we see that at time 2, P3 arrives. Now what is the burst time of P3? It is 9 milliseconds. But 9 milliseconds is greater than P2's burst time, which is 4 milliseconds. So we are not going to preempt P2 because P2's burst time is still lesser than that of P3. So P2 will continue its execution. Now we see that P3 arrives at time 2. Now what is the burst time of P3? It is 9 milliseconds. So we are not going to preempt P2 because P2 is using the CPU, and even though P3 has arrived, the burst time of P3, which is 9 milliseconds, is greater than that of P2. So P2 is still having the lesser burst time. So P2 will still continue its execution and it will not be preempted. Now we see that at time 3, P4 has arrived. Now P4's burst time is 5 milliseconds. So P2 will not be preempted and it will continue its execution. Now another thing that you have to keep in mind here is that, see, when P3 arrives, the burst time is 9. Now we cannot say that at that moment the burst time of P2 was 4 milliseconds because P3 arrived at time 2. Now let us look at this chart and see what is the condition of P2 at 2 milliseconds. So P2 got the CPU at the first millisecond, and at the second millisecond P2 has already completed 1 millisecond of execution. So the remaining time of P2 is now 3 milliseconds. So it is not 4. But at time 2, P2's burst time will be 3 milliseconds because it has already completed 1 millisecond of execution. So similarly, when P4 had arrived, it was 3 milliseconds time. So at 3 milliseconds, what was the condition of P2? P2 had already gone from 1 to 3. So 3 of its execution was already completed. So 1 to 2, 2 to 3. So at the third millisecond, P2 already completed 2 milliseconds of its execution. So the remaining time is again 2 milliseconds. So from 3 to 4 and 4 to 5. So that was the remaining time of P2. So you have to keep this in mind when you are doing this for more processes or when the processes have a very small difference in their burst times. Alright, so we saw that even though P3 and P4 had arrived when P2 was executing, since their burst times were greater than that of P2, P2 was never preempted. So P2 had completed its execution at the 5th unit of time. The burst time was 4. So 1, 2, 3, 4. 1 plus 4 is 5. So at the 5th unit of time, P2 has completed its execution. Alright, now since P2 has completed, now the question is who will get the CPU next? Now we have P1, P3 and P4. Now who is going to get the CPU now? So let us see. What is the burst time of P1 now? It is not actually 8 now because P1 already completed 1 millisecond execution in the beginning. So the burst time of P1 is now 7 milliseconds. Keep that in mind. And P3 and P4 never got the CPUs, so their burst times are 9 and 5. So here we have 7, here we have 9, here we have 5. So which is the smallest one? It is 5. So that is of P4. So P4 is the one to get the CPU next. So when P4 gets the CPU, it executes from 5 to 10 milliseconds because the burst time is 5. And we know that no other processes have arrived after that. So it will just continue its execution and finish it. So 5 plus 5 is 10. So at the 10th millisecond, P4 finished its execution. Now what is the next thing that we have? We have P3 and P1. So what is the burst time of P1? I told you here it is 7. So P1 is 7 and P3 is having 9. So which is smaller? 7 is smaller. So now P1 will again get the CPU. So P1 gets the CPU and the time it needed was 7 milliseconds. So from 10 to 17, 10 plus 7 is 17. So up to the 17th millisecond, P1 executed. And then the last one that we have is P3, which is of 9 milliseconds. So at the 17th unit of time, P3 got the CPU and it executed for 9 milliseconds, hence completing its execution at the 26th millisecond. So this is how the Gantt chart for this set of processes looks like. So we see that preemption occurred here. P1 was the first one to get it, but since a condition arose where the burst time of the next process P2 was less than that of P1, so P1 was preempted and the CPU was given to P2. And then later on when P1 got its chance, it was given the CPU again. So that is what we mean by preemptive scheduling. And this is how the Gantt chart will look like for the SJF scheduling when it is preemptive. Alright, so now let us see how we can calculate the average waiting time for this SJF scheduling algorithm when it is preemptive. So in the previous example, it was very easy to calculate the waiting times because we assumed that all the processes arrived at the same time and they were non-preemptive. So we had to just look at the Gantt chart and write down the waiting times for each of them and calculate the average waiting times. But in case of this preemptive scheduling, it is not going to be like that. For this SJF scheduling, there is a specific way to calculate the average waiting times. So let us see what is the formula that we have to use and how it is going to work. So here is the formula that we have to use. Waiting time is calculated like this. Total waiting time minus number of milliseconds process executed minus the arrival time. Alright, so this is the formula, and let us try to see how this formula is formed. Let us break it down and try to understand. So the waiting time is the time that a process spent waiting. So that will be the total waiting time that we can see from the Gantt chart minus the number of milliseconds the process executed. Because we saw that since this is a preemptive scheduling, there may be times when the process has already executed. Like in case of this P1, it executed for 1 millisecond in the beginning. Then after that it was given again, and then it completed at 17 milliseconds. So here you see that at the 10th unit of time, or at 10 milliseconds, P1 got the CPU. So the waiting time of P1 cannot be just said as 10 milliseconds because it has already executed some units of time over here. So 10 cannot be considered as its real waiting time. We have to subtract the number of milliseconds it has executed previously. And then we have to also subtract from it the arrival time, because not all processes arrives at the same time. So from these two values, we have to again subtract the time at which the process had arrived in the ready queue. So that is how we will find the waiting time for processes in case of a preemptive SJF scheduling algorithm. Alright, so applying this formula, let us try to calculate the waiting times for these four processes and also the average waiting time. So here is the waiting times of these processes P1 to P4 based on this formula. So for P1, what is the total waiting time? If we look at the Gantt chart, for P1, the total waiting time was 10 milliseconds. So it is 10 minus the number of milliseconds the process executed. So prior to this, how long did P1 execute? If you look here, P1 executed for 1 milliseconds over here. So minus 1. And then the arrival time. What is the arrival time of P1? It was 0. So minus 0. So if you subtract 10 minus 1 minus 0, we get 9 milliseconds. That is the waiting time for P1. Now let's see for P2. What is the total waiting time for P2? So we see that for P2, it got the CPU at 1 millisecond. So 1 was the total waiting time for P2. Then how long did P2 execute before that? So we see that P2 did not execute before that at any time. So it is 0. And what is the arrival time? Arrival time of P2 is 1 millisecond. So 1 minus 0 minus 1, which is 0 milliseconds. So P2 did not have to wait for any time. It is 0 milliseconds. So see, if you look at the Gantt chart, we may think that P2 waited for 1 milliseconds. But if you really analyze it, you'll see that though P2 arrived at time 1, since its burst time was less than that of P1, it was preempted. P1 was preempted. And as soon as it arrived, P2 got the CPU. So that is why the waiting time is 0. Now similarly for P3, what is it? The waiting time for P3 in total was 17 milliseconds. And what is the number of milliseconds it executed before? There is nowhere when P3 executed before. So that is 0. And what is the arrival time of P3? It is 2 milliseconds. So 17 minus 0 minus 2 is 15 milliseconds. And similarly for P4, 5 milliseconds was the total waiting time. If you look here, P4, this is the total waiting time. And then did P4 execute anywhere before? No. So it is 0. And the arrival time of P4 was 3 milliseconds, which is given here. So it is 5 minus 0 minus 3, which gives us 2 milliseconds. Now if we calculate the average waiting time, 9 plus 0 plus 15 plus 2 divided by number of processes, which is 4, gives us 6.5 milliseconds. So this is the average waiting time in case of a preemptive SJF scheduling algorithm. So we see that in SJF scheduling algorithm, when it is preemptive, who is getting the process first? The process that has the next smallest remaining CPU burst is the one to get the CPU next. So whichever process is having the next smallest remaining CPU time. Why do I use the term remaining? Because since it can be preempted, once a process is already executed, and if it is preempted, the remaining time is what we have to calculate, like I explained in the beginning. So the process that is having the least remaining time, or the least remaining next burst time, will be the one to get the CPU first. So preemptive SJF scheduling is sometimes called shortest remaining time first scheduling. So this is another name that we have for preemptive shortest job first scheduling. It is called shortest remaining time first scheduling. And why is that? I have just explained that. Alright, so we saw that SJF scheduling algorithm is good and it is performing well, but does it have any disadvantages as well? Let us try to find that out, and let us see what are the disadvantages of this SJF scheduling algorithm. So here we will discuss the problems with SJF scheduling. So the problem is, the real difficulty with the SJF algorithm is knowing the length of the next CPU request. So we saw that SJF scheduling algorithm is the one in which the process having the next smallest CPU burst will get the CPU first. But it is very difficult to know the length of the next CPU request. It is not very easy to find out what will be the next burst time of the process. We may be able to somehow find out the entire length of a process, but the next CPU burst of the process, that means the next time it is going to use the CPU, what is the amount of time it will take? It is very difficult to calculate that particular value. So because of that, although the SJF algorithm is optimal, it cannot be implemented at the level of short-term CPU scheduling. So even though this is an optimal algorithm, as we have seen, it is difficult to implement this at a short-term CPU scheduling level. And why is that? That is because of this. It is really difficult to know the length of the next CPU request that we are going to get. So practically, there is no way to know the length of the next CPU burst. So this is one problem that we have with the SJF scheduling algorithm. So you may be thinking, if we can never know the length of the next CPU burst, how are we ever going to use this SJF scheduling algorithm? So there are ways to still use it, and let's see how it is. So what we are going to do is, our approach is to try to approximate the SJF scheduling. Now how are we going to approximate it? So we may not know the length of the next CPU burst, but we may be able to predict its value. So we may not know what is the length of the next CPU burst. Exactly, we may not be able to know it, but there are ways we may be able to predict or assume its value. That is, we expect that the next CPU burst will be similar in length to the previous ones. So once one CPU burst has occurred, then we can assume that the next CPU burst also will be approximately of that same length. So in some cases it may not be the same, but in most of the cases the next CPU burst will be somewhat similar to the previous CPU burst that we have. So we can approximate the value in that way and use the SJF scheduling algorithm. So by computing an approximation of the length of the next CPU burst, we can pick the process with the shortest predicted CPU burst. So with this approximation, we can pick the process with the shortest predicted CPU burst, and then hence we can apply the SJF scheduling algorithm in this. So that is how this problem with SJF is resolved. So that is how SJF scheduling algorithm works, and we see that it is better than FCFS scheduling algorithm, but also it has its disadvantage or problem which we have just discussed. But there is also a approach to resolve this problem. It may not be the best approach, but there is still an approach to solve this problem. So I hope this lecture about shortest job first scheduling was clear to you. Thank you for watching, and see you in the next one.